Okay, in this video, in this lecture, we're gonna shift gears quite a bit. We've been looking at derivatives of various functions. Well, first of all, we define the derivative, we deduce some properties of it, we deduce some rules and laws that allowed us to compute derivatives more easily. So we looked at like addition rule of differentiation, that is that the derivative is a linear operator, and we looked at the product rule, the quotient rule, then we looked at derivative of trig functions, and then we were able to finally get chain rule, and that's allowed us to do implicit differentiation and get derivatives of inverse functions. So now we're going to kind of like we're not going to look at we're not going to deduce any more general rules about derivatives. I think we, for the most part, developed enough theory. Maybe we'll develop some more ideas in chapter 4. So now we're going to shift gears, as I said, and look at some applications um, of derivatives. So these are just going to be some partial applications. We'll see some more applications in chapter 4, in particular when we get to optimization. So in this lecture, we're going to cover section 3.9. This is on related rates. So basically the idea is that you're going to have multiple quantities, all depending on some common quantity. So usually that is going to be time. So for example, we're actually looking at an example where we have um, this balloon, which we can assume is perfectly spherical. And then we have the quantities of volume and radius. And these things can, and we're going to have air being pumped into the spherical balloon. And so the quantities of radius and volume are going to depend on time. That as time passes by, the volume is the radius is going to increase, which is going to correspond to the volume increasing. So the radius and the volume are going to be functions of time. We're going to model them as functions of time. All right, so let me share my screen. So hopefully you can see what I'm seeing. Um, so we're going to use chain rule, and we're going to use the basic idea is implicit differentiation, and then we're going to use things like chain rule and product rules and quotient rules, possibly, but mostly just implicit differentiation and chain rule. So let's just jump right into an example. All right, so let me uh, pull the example up. I don't want to pull the whole book up. I just want to pull this one example up and work through it together, or work through it with you, I guess. Um, so let's see. There we go. So here's example one. So we are being told that air is being pumped into a spherical balloon, um, so that its volume increases at a rate of 100 cubic centimeters per second, and we want to figure out how fast is the radius of the balloon increasing when the diameter is 50 centimeters. So usually we have, as I said, these sort of related rates problems, multiple quantities depending on a single quantity. So in this case, volume and radius, and they depend on time. But these quantities also have some sort of relationship between them. That's the name. That's why we get the name of this section, related rates. So we have rates at which radius change and volume change with respect to time. But then there is a relationship between those, the rate at which volume changes and the rate at which radius changes, because there is a relationship between the volume and the radius. And that's going to be a common theme, basically figuring out exactly what that relationship is. So the to best way to proceed in this problem is to start setting up some notation. So what we'll do is we're going to let V represent volume of spherical balloon. And we're going to think of it. So it's thought of as a function of time. So it's some function of time. We don't know, maybe we don't know exactly what sort of function it is of time, but we do know um that how it's changing with respect to time. It's the volume is increasing at a rate of 100 cubic centimeters per second. So whatever function v is, we at least know the rate at which it's changing. And it turns out that's all we need to know to figure out how the radius is changing or increasing. We only need to know the rate. We don't need to actually know what those functions look like. So we're gonna let V be the volume. So if you want, you can even just like replace this with like V of T if you want. Not entirely necessary, but just remember that. And if you just so that you can remember that's function time, certainly use this notation if you need to, but it's not completely necessary. And then we're gonna let R be the radius of the spherical balloon. And again, we're gonna think about it. Whoops. Think about it as a function. Oops, I did thought of place over here. So thought of as a function of time. So both of these are functions of times. And again, if you want, you can actually just kind of replace this with RFT just to emphasize that if you want. All right, so now given that, so now we set up some partial notation, and let's try to re-express things, the givens, in terms of this notation. So what we're given, and just to remind you, this is section 3.9. So if you want to follow along in the book. So what we're given is that the rate at which the volume changes, so that is the derivative. Remember, derivative gives you a rate of change, and that's with respect to time. So it's dt, not dx, but dt. I mean, you can let x denote time if you want, but it's usually just better to use t to represent time. So we're given that the volume is increasing at a rate of 100 cubic centimeters per second. So this is instantaneous rate of change of volume with respect to time. So this is what we're given. And this is and then is the unknown is so let's go back and figure out what the unknown is. So we're, as I said, air is being pumped into a spherical balloon, so its volume increases. And that's important that we're using the word increases at a rate of 100 cubic centimeters per second. So increasing means derivative is positive. It's like you're adding more and more volume every second. You're adding, and specifically, you're adding 100 cubic centimeters to the current volume of the balloon every second. That's one way to think about the derivative, is that every second you are adding 100 cubic centimeters of air into this balloon. So you want this number to be positive. Negative would mean that it's decreasing as every second you are losing 100 cubic centimeters of volume from the balloon every second. So it's important that the derivative is positive. We'll see that sometimes that this derivative is going to be negative depending on the problem. And so what is the given? We want to know how fast the radius is changing of the balloon when the diameter is 50 centimeters. So if now I should have written this up here. Recall, this is called kind of out of order. Let me see how do I. In fact, let me before I write down these givens and unknowns, let me get rid of this for a second. Throw this to the side and delete it. So now, so let's say note if diameter is 50 centimeters at some point in time. And notice it doesn't say what the point in time it is. It's just saying at some point when the diameter is 50 centimeters, we want to know how fast is the radius changing at that. So we don't know when it's changed. We don't know when the diameter will actually be 50 centimeters, but at some point in time it will be. So if the diameter is 50 centimeters at some point in time, t if you want to call it, or t zero, whatever, you can give that time a name. Some point in time, you can call it t zero if you like. Sometimes it's like it's never all it's sometimes it's useful to like, or I don't want to say useful, but sometimes it can be helpful to give names to every quantity. Like you can call this time point in time when the diameter is 50 centimeters t zero. You might end up using that fact that it has this name t zero, but you never know. So it doesn't hurt to give names to everything. It's going to turn out that you don't really need to know what the time is, but it's always good to just write this stuff, everything down if you can. So when the diameter is 50 centimeters at some point in time, the radius is going to be, well, the relation, there's a relationship between the diameter and the radius, and the diameter is also a function of time. The diameter is going to be changing as time passes, and it's just going to be half. The radius will be half of the diameter, so 25 centimeters. All right, so now we can go back to what I was writing. So what is given and what is unknown? So we've set up this notation to describe the various quantities in this problem, and now we want to use this notation. This is the whole point of mathematics, is to give, yeah, I give you a real world concrete problem, and you want to mathematically describe this problem. You want to set up some notation. You want to make this problem more precise. And so you do that through notation, mathematical notation. So, well, let's use our notation. So we're given that the volume increases, as I was pointing out before, it's increasing at a rate of 100 cubic centimeters per second. So that is the derivative. If we're told the rate at which the volume is changing with respect to time, you should automatically think derivative. And because it's increasing, it's going to be positive 100 cubic centimeters. And of course, we don't write the positive. So this is what we're given. So we're told that the volume is increasing at a rate of 100 cubic centimeters per second. So that's derivative. Think derivative. And then the unknown is, what is the unknown? Well, we don't know. We want to know what the rate at which the radius is changing when r is equal to 25 centimeters. So we want to know what the radius is at basically t zero, that time t zero. We're not going to end up using this notation, but basically we want to know what is the rate at which the radius is changing, the instantaneous rate of change. Remember, that's the whole point of calculus, to describe make sense of the notion of instantaneous rate of change. We want to know what is this derivative. So now the only thing we need is we need a connection between dv dt and dr dt, so that we can describe this unknown in terms of this thing that is known. Well, we have such a relationship. So volume of sphere, we have the volume of a sphere, and that is that the volume of the sphere is 4/3 pi r cubed. So now this doesn't directly relate dv dt and dr dt, it relates v and r, but that's okay because um, all we need to do is implicitly differentiate this with respect to time. So if we do that, then we will get that relationship that we want. And this is the point of the whole, this is the sort of why we call these problems related rates, because we have some equation or relationship between the quantities that both depend on some common quantity, which is in this case time. So now we differentiate this. So we're going to apply the derivative operator to both sides. 4/3 pi r cubed. And now, so the left-hand side is just going to be simply dv dt because we're taking the derivative of just v. Now on the right-hand side, so first of all, we have these constants, 4/3 pi, so we can take those out of the derivative, right? And now we're going to take the derivative with respect to time of r cubed. And r is a function of time, so we got to think, right here, we need to think chain rule. Because we have basically r, which is our inside function, composed with this cubing function. So we can think of r cubed is r, which you can think of as r of t. It's a function of time composed with t cubed. Oops. So we have a composition of two functions of t, right? So this is going to be the inner function, the inner piece or the inner function. This is going to be the outer piece or the outside function. I think I was saying outer. Maybe I'll say this would be the inner function. This would be the outer function or the outer piece. All right, so now we just do chain rule. So the chain rule says we have 4/3 pi. And the chain rule says you take the derivative of the outside function, which is t cubed. So it's going to be times t. And then it's going to be, and then you reduce the 3 by 1. But then you have to evaluate it at the inside function. So it's going to be 3r squared. And now you take the derivative of the inside function and you multiply it, which is dr dt. And then you can simplify a little bit. So, sorry, these threes right here cancel. So you get 4 pi r squared dr dt. And this is what we want right here. So solve, we're going to just solve for this piece right here. So dr dt, whoops, is going to be 1/4 pi r squared dv dt. So remember what are we given? We're given dv dt is equal to 100 cubic centimeters per second, and then r is equal to 25 centimeters. So that implies when we plug everything in, we get that dr dt, the rate at which the radius is changing, is 1/4 pi r squared. So 25 cubic centimeters squared times 100 cubic centimeters squared. Sorry, I think I said cubic over here, just 25 centimeters. And so at this point, let me drag this down a bit. You get dr dt is equal to 1/4 pi. I guess what is 100? Let's see. I guess okay. So this will be 25 squared times so 25 squared squared centimeters times we'll just say 2 times 25 cubic centimeters per cubic centimeters per second. And then let's see, so this 2 cancels the 2 over here, and then we have a factor of 25 here and another one here. So, and then you can cancel centimeters squared with centimeters squared over here to get just centimeters. And I guess if you just do all of that, you get 1 over let's see. Actually, I'm looking at the book and it doesn't seem, I must have done something not quite right. Like that doesn't seem. Why isn't it 50? Let's see. No, this is all right. I guess it just reduces to 1/25 pi centimeters per second. Why is that? That's all right. Let's put this all in one numerator. 2/25. I'm going to ignore the units for a moment. Times 25 squared. So this is 1/2 pi times 25. Why isn't it? So why isn't it 1/50 pi? I'm confused. I feel like this might be an error in the book. Anyways, the last number doesn't really matter a whole lot. Hopefully the rest of the problem made sense, and I don't. So I'm really confused as to why. All right, let me pull up the book for a second. Oops. And maybe I'll do this in. All right, why is this happening? I don't understand. So it'd be 100 divided by, let's see, 4 pi 25 squared. 4 times pi times 20. Oops. 4 times pi times 25 squared. Oh, it is 1/25. I don't understand. Oh, I know why. Because I can't do arithmetic. That's why. I wrote. Okay, I know my problem. I know the problem. Anyways, it is 1/25 pi. What I did right here was a mistake. It's 100 is definitely not 100 is definitely not 2 times 25. So that's not right. It should be like, I guess it would be, oh yeah, I know the problem. Uh 100. Yeah. I make so many arithmetic errors, it's ridiculous. 100 is gonna be 4 times 25. So that's why we get the fours cancel, and then so the fours cancel, a factor of pi can't, so 25 cancels, so you get 1/25. Okay, that makes sense now. Sorry about that. So this is the final answer right here. All right. So let's look at another example. All right, so we have, let me snip this example. So a new one. All right, so the next example is number 2. Let's see, can I put it there? Put it right here. So example 2, let's make it a little bigger though, is that we have a ladder, a 10-foot long ladder rests against a vertical wall. And then we're told that the bottom of the ladder slides away from the wall at a rate of 4 feet per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So at some point in time, the bottom of the ladder will be 6 feet away, and we want to know what the rate of change is of the top of the ladder at that point in time. All right, so now I think the best way to proceed is always set up, draw a picture if you can. If you can draw a picture, always do it. So let's see if I can get one. So basically what we have is we have the following setup. So maybe the wall goes up a little bit longer and then the ground goes further this way. So the ladder, here's like the top of the ladder, here's the bottom of the ladder, and we're told that this is 10 feet, the length of it, so it's fixed. And then we have these two lengths right here that are changing with respect to time. So as the ladder, we're told that the ladder is sliding down like this. So this distance from this point to this point is changing with respect to time. So give it a name. Let's call, and the most natural thing is to call it y, because I mean, look at what we've drawn. We basically draw an xy coordinate plane. So we'll call this y. And again, similarly, as this like you can think of this as a bead sliding down. As this slides down, this point right here gets pushed this way. So this distance right here from this point, the origin, if you will, to this point is changing. So call it x. So um, x and y are functions of time. We can think of them as functions of time. So now what is given? Let's just identify what is given. So what we're given is that these we're told that the bottom of the ladder slides away from the wall at a rate of 4 feet per second. So in other words, like this point right here is sliding this way 4 feet per second. So and x represents how far this point is from our origin. So that's what's changing with respect to time. So what we're given is that dx dt is 4 feet per second. And then what is unknown, or what are we trying to find? We're trying to find what we're trying to find is how fast how fast the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet from the wall. So we want to know what is dy dt. What does that equal to when x is equal to 6? When the bottom of the ladder is 6 feet from the wall at some point in time. And again, you can give it a name if you want. T0. We want to know what this is. Now, here is something we should expect. So as this point is sliding along, this distance right here from the top point here to the origin is shrinking. It's getting smaller, right? This point right here, maybe it will end up here. So this distance from here to here is shrinking. This number y should be shrinking. And so when this point right here goes down here, this point might be like further along here. And then you like basically have this smaller triangle, or not, this narrower triangle, I should say. So what we expect is that dy dt is negative. It should be a negative number. So this is like it's always good to write down what your expectation is, or what your conjecture is. Because if you get something that is contrary to what you expect, that should be an indication that you maybe did something wrong. So these are like consistency checks, basically, like just based on the physical setup of the problem, this is what you would expect. That the y coordinate is since the y coordinate is shrinking, it's getting smaller because this point is moving closer to 0. We'd expect that rate of change to be negative, because it should be decreasing every second. In other words, you should be subtracting for every second that goes by, you should be subtracting some number from this initial y coordinate right here. Think about when you're accelerating, or when you're accelerating. If you're slowing down, your acceleration is negative because you want to reduce your speed every second, right? You're subtracting some number from your velocity every second, which corresponds to you accelerating basically in the negative direction. You're subtracting. So we expect this to be negative. So if we don't get a negative number, that means we did something wrong. So we have these two quantities, and we're given this, and we want to find this. So we need some sort of relationship between them. So we need to relate dy dt and dx dt. Well, how do we do that? Well, let's go back to the drawing. What is this drawing right here? It's a triangle, right? In fact, it's a right triangle. No, setup corresponds to right triangle. So we know the relationship between x and y. um, since x and y represent side lengths of a right triangle, which is changing with time. The triangle itself is changing with time, which is changing with respect to time. X and y satisfy Pythagorean theorem or the Pythagorean identity, whatever you want to call it. Let's say Pythagorean identity. That is x squared plus y squared is equal to the radius squared. The radius is one, that's going to be 10, so 100. It's going to be 10 squared, so it's 100. All right, so we have x and y are related by this equation, so we can just implicitly differentiate. Differentiate with respect to time. So when you do that, so we have x squared and y squared, and x and y are functions of time, so we have to use chain rule. We have a composition. We have x composed with t squared. We have y composed with t squared. So x and y are inner functions in this case. So we're going to apply the derivative operator to both sides of the equation. And the left-hand side is going to be 2x dx dt plus 2y dy dt. And then the right hand side is just going to be 0 because we're differentiating constant. And that basically corresponds to the fact that the length of the ladder is not changing with time. It's just a constant. Of course, you can imagine maybe a more complicated situation where you have like the ladder is exposed to increasing temperatures with time. So maybe that affects the length of the ladder. So you can imagine you can make these problems as complicated as you want and maybe more realistic or whatever. But we're just going to assume that the temperatures are relatively constant, so the ladder length of the ladder doesn't change. So that's why this is going to be 0 on the right hand side. And then what we're trying to find is this right here. So let's solve for it and see if we can actually figure it out. So when you do that, you subtract when you do this simplification, you're gonna get negative x over y dy dt. And notice this is we divided by y, but that's okay because we're not the ladder is never gonna perfectly lie on the ground. So the y will actually never really be 0. So let me create some more room. All right, so we have that x is equal to 6. Well, there's a kink now because we have this y in this formula. But we can use the Pythagorean theorem again to figure out what y has to be when x is 6. So we have 6 squared plus y squared is equal to 10 squared. And when you do this when you simplify and solve for this, you'll get that y is equal to 8. And you're going to take, it's only going to be 8. There's not going to be a plus or minus because X and Y represent lengths. So you can't have negative feet, for example. So then this implies that dy dt is going to be equal to -6/8, and that's good. Notice we have a negative here. And this is good because X and Y are both going to be positive, and we're given, oh, I'm sorry, I wrote dy on the right hand side. It should be dx. X and Y are going to be negative, are positive because they represent side lengths. So we have a negative times X over Y, which is positive, and we're given that this is positive. So this kind of like, we have this consistency, we have this expectation satisfied. We have this, we're able to make sure that everything is consistent. So we are in fact going to get a negative number. So we get -6/8 times, so this is 6 feet over 8 feet times 4 feet per second. And when you simplify that, you're going to get -3 feet per second. So this is good. We got a negative number. So this is a good sign that we have the right number, assuming we didn't screw up some calculation somewhere. And so let's just go back to this formula because this is interesting right here. So X and Y are always going to be positive numbers. So really what's controlling the sign of dy dt is this term right here. So let's imagine now that instead of dy dt being, dx dt being positive, meaning you're sliding away from the wall, dx dt is negative, meaning you're pushing the bottom of the ladder towards the wall. So if that's what if you're going back to our picture, if this point right here is now being pushed towards the wall, we would expect that this point is now being pushed up against, it's like sliding upwards now. So we would expect dy dt to be a positive number. This, because that means that this length right here, this side length y is increasing. So we're adding more feet to we're adding more feet to that length every second because we're sliding this point up closer against to this point. So dx dt will be negative. This term will be negative, and it will cancel with this negative to give dy dt is positive. So this is really shows that this is going to be the right formula, and it's consistent with the physical setup, in other words. So it's always good to have these like mental models that correspond to like physical models, what's actually, or rather, these mathematical models actually are in fact consistent with the physical setup, or consistent with the thing which you're trying to model. So you have this physical intuition about what's going on, and it should match up with your mathematical model. All right, let's look at, I think there's maybe one more problem. Yeah, we'll do one more problem. So let's see. I'm gonna pull open the book this time because there's a picture, and I know I'm gonna screw it up. So we have this problem right here that a water tank has the shape of an inverted circular cone. So water tank, whoops, the shape of an inverted circular cone with base radius 2 meters and height of 4 meters. And then the water is being pumped into the tank at a rate of 2 meters per second, so meters cubed per second. And we want to find the rate, so we want to find the rate at which water level is rising when the water is 3 meters deep. So again, always draw a picture. So here's our inverted circular cone. And so at some point in time, maybe you have this height, the water level is at this height, and it will correspond to this radius right here. And then we're told that the base of this cone, which is really the top of the cone, is 2 meters right here. and then in total, it's the height of the cone is 4 meters. So what we want is what we're given is the rate at which the volume is increasing. So we have dv dt, and we want to find dh dt. So the v and the h are functions of time, and also the radius is as well. So we have that the volume we can, and we want to find, we want to relate these quantities right here. So we can solve for dh dt. That's what we want to know. We want to know the rate at which the water level is rising. That is the height of the water level. So we have a relationship between d and v and h, and it's given by this equation right here. But the problem is, we don't know really anything about r, so we want to eliminate r. And so we're going to use this trick about similar triangles right here. So there's a similar triangle situation going on here. So imagine we have this point right here, and we have two triangles with one inside the other. So we have this triangle right here, and then we have the bigger triangle, and they share basically sides right here. Maybe I should have done a different color actually. Let's see. And then we got, whoops. Then we got like this thing, this bigger triangle right here. So because they are similar, that is they share a common angle right here, we know that the ratio of their sides has to be equal. So the ratio of the yes, the ratio of their side lengths has to be equal. So this r right here divided by this h right here, r over h, has to be equal to this side, this side length divided by this side length, or the other way. It doesn't matter. You could do 4/2 and then h over 4 r, or r over h and 2/4, and then that allows you to eliminate h in sorry r in this formula, because notice there's a v, r, and an h. But we can get, as I said, get rid of the r. And then when you do that, so you have this r right here, you're going to replace it by h over 2, and you're going to square it. So you do the simplification, you can see that v is equal to now pi over 12 h cubed. So we've completely eliminated r, which is good because we don't really know much about r. We don't, and we're only given things about h and v. And now we're going to implicitly differentiate. We're going to differentiate v, which is equal to pi over 12 h cubed. So on the left-hand side, we just get dv dt. And then by the chain rule, we have to differentiate. We have this constant pi over 12, but we can just take that out. And we have this, by the chain rule, we want to differentiate h cubed. So we bring the 3 down. Let me just do it out, because they do leave a step out. That's going to be pi over 12. And by the chain rule, it's going to be times 3 h squared dh dt. And now that's going to be, the 3 is going to cancel with the 3 and the 12. So you get pi over 4 h squared dh dt. That's how they get this line right here. And then you can solve for dh dt to get this. And then you just plug everything in, because we know h and we know dv dt. Remember, up here. We are told that dv dt is 2, basically. And then we want to know what dh dt is when h is 3. So h is 3, dv dt is 2, so you plug those in and you get that. So I think that there, I don't think I'm going to go over 4. If you want, I think there's 2 more examples, but I think we've done enough. But if you still need more practice with these, I encourage you to go through 4 and 5. Work through the details, and of course, if you need help with them, just reach out to me. and we can figure it out over email or we can meet via Zoom. So that's all for today, though, or for this lecture, I should say.